Generally, refineries receive crude oil, and this crude oil gets converted to white products like petrol, diesel, air traffic fuel. We are engaged in a project where refinery assets were repurposed to refine used vegetable oil and fat to produce biofuel. Utilizing existing refinery to produce biofuel brings new challenges to protect assets and expensive catalyst. A known solution is to create a temperature profile of your reactor. To explain in detail, I will take you to Stefano Mella and Michele Pietroni.
Hello, Janish. Today we would like to discuss about a very interesting case study, which is about isomerization process, but starting from edible oils and not from fossil fuels. More specifically, we would like to discuss about how to comply with the technical specification of this isomerization process. And second one is about how to increase the process throughput. I'm not alone, I'm together with Mr. Michele Pietroni, our industry manager for chemical and oil and gas at Enders&Hauser Group. Hello, Michele.
Hello, Stefano. Thank you. So, Stefano, as the expert for temperature measurement, so how would you deal with applications used to produce sustainable fuels like biodiesel that apparently look like hydrocracking, which is used to produce fossil fuels? So, specifically, how would you met requirements belonging to three main areas? So requirements regarding the reactor internals design, requirements regarding the where the temperature must be detected, and requirements regarding the wetted materials. So materials which are used for the internals of the reactor. So how would you phase with these groups of requirements?
Interesting. Three very interesting points, but please let me better understand what is the difference between standard hydroprocessing or isomerization processes and this one coming from edible oils.
Okay, so when I mean requirements regarding the design of the internals, you should know that the process temperature must be detected in a very small volume, which is between a catch box and a redistributor tray, which is full of small chimneys, which are equipped with two small holes each. So you should even know that in this volume, hydrogen is also injected in order to cool down the process fluid, carrying a mixture of two phases, the liquid phase and the gaseous phase. So basically in this volume you have two phases, one together in a small volume.
Okay, and how do you deal with these B phase fluids then?
So you should know that the liquid phase is kept under control, and the small holes are used to keep always at the same level the liquid phase at a certain threshold. So basically, you have, or we have in this application, to avoid that the fluid goes down from the top to the bottom of the redistributor tray. So it means that the process fluid must not be sprayed as a liquid by the chimneys, but must be distributed as a gas.
And where do you measure the temperature then? Is it inside the catalyst or not?
The catalyst has nothing to do with the temperature measurement. So the main target is to detect temperature inside the small volume above the small chimneys, and the temperature must be detected, okay, there, and must be detected as a steady temperature, always at the same level, at the same value.
That's interesting, and this reminds me a very recent application we had with a customer. They were also interested on measuring the temperature just on the top level, close to these chimneys, and not inside the catalyst. So in a two-dimensional way and not in a three-dimensional way.
So very interesting this case, and was the temperature the only parameter on which the customer was interested on?
No, it was not the only one. They were also interested on measuring the pressure, and that's because by acting on temperature and pressure, they could change the stoichiometric parameters and therefore influence the process efficiency.
Okay, okay. So coming back to the now to the third group of spatial requirements. What about the materials? So from the drawings, I see that the reactor material are overlaid by alloy 625, which is a very high corrosion resistance alloy. So may we supply or may we comply with these special alloy characteristics?
Absolutely.
Yeah.
We can provide the thermometers with the stainless steel materials, which are for us common materials, but also different materials like alloy 625, more exotic, but also more resistant when it comes to corrosion.
Okay. So I think that okay, we have analyzed all the three basic requirements on this application. So the design of the reactors, of the internals, so where detect temperature, and so how to comply with the special materials. And how would you sum up the solution in terms of temperature measurements for these kind of applications?
Yeah, I would say that we can for sure meet the requirements of these new processes, and also that the materials are for sure not an issue. And I would also like to take this as an opportunity to remind that when it comes to safety of the processes, we can also provide thermometers with diagnostic features. And we have a long experience in installation and commissioning to install in the proper way our instruments. And last but not least, the long experience we have in the oil and gas and chemical industry will for sure support us in this transition phase of these processes.
Okay, very nice conversation. Thank you very much, Stefano, for exchanging.
Thank you very much, Michele. And then
Okay.
back to the studio.